Okay, now, we're going to talk about a special property that an operator can have, and it is called its kernel, also known as its null space. Okay, those two words are synonymous. I'll use both terms. I like kernel better because I like popcorn, but null space is used too, so I'll probably go back and forth between the two. But kernel and null space mean the same thing, just so you know, right? The kernel of a matrix, and what exactly does that mean? So first of all, we're talking about a linear operator here. So it's a square matrix. It is a matrix which will translate a point in n-dimensional space to another point in n-dimensional space, right? So it's a square matrix. And let me just sort of motivate this. Let's take an example in our two-dimensional case. Remember we had this matrix here, which was negative 1, 0, 0, 1. And this was our flip across the y-axis matrix. That's what that linear operator did, because if you remember, we said, well, if we have the point 3, comma 4, this thing is going to translate it 3, 4 into negative 3, 4, right? And so basically this thing is moving it across the y-axis, and that's the function of this matrix here, right? Okay, so now here's my question. One question we could ask is, what happens if I multiply this by the 0 vector? And it doesn't take a rocket scientist to realize that you're going to get the 0 vector back, right? Because no matter what you dot product with 0, I don't even need to look at the matrix, actually, to know that's going to give me 0. And if I take the bottom row, whatever it is, times this, I'm obviously going to get 0. So it doesn't take a brain surgeon to know that if you multiply any matrix by the 0 vector, you're going to get the 0 vector back out. Now, one question that we might ask is, are there any other vectors that we can multiply that thing by and get the 0 vector? That's going to turn out to be interesting and important. It's not obvious now why it would be, but it will turn out to be later. And here's the definition. The set of vectors that a matrix will translate or map or transform into the 0 vector is called its kernel, or its null space, okay? The set of vectors that it maps to the 0 vector is called its kernel. So if you go back to this example here we were looking at, you might ask yourself, is there anything else besides 0, 0, which obviously is going to give us 0? Is there anything else that will give us the 0 vector? And you realize that you can think of that in a matrix way like we did. You can also think of it as an operator way. So if this is the matrix A, we're basically saying, you know, this thing's going to translate points in R2 to the points in R2. So really I'm saying, what is the set of all vectors V such that A, when operated on V, gives us the 0 vector? That's really what I'm asking. That's really what the null space or the kernel of a matrix is, okay? Now, if you look at this matrix here, you'll realize that the answer is no. There isn't anything except the 0 vector itself that it will take to the 0 vector here. And you can see that because geometrically what's going on, right? If it's taking every point and flipping it across the y-axis, it's taking points over here and flipping them over there, it's taking points over here and flipping over here. If that's what this thing is doing, well, ask yourself, how could you ever get to the 0 point unless you started on the 0 point? Because if you started anywhere above or below the 0 point, you're not going to end up on the origin because you're not changing your y value by this operation, right? And if you started anywhere over here or anywhere over here, you're going to be flipped to the opposite side. You're again not going to end up on the origin. So you can pretty easily convince yourself that the null space of this operator is simply the 0, 0 vector itself. This is set notation right here, right? So I'm saying the null space of A, or the kernel of A, is this thing right here. And sometimes mathematicians will say ker A equals that. And that basically means the kernel of A is the set of nothing more than the 0 vector there, right? And if you consider some of our other examples, like we had this example, 0.707, negative 0.707, 0.707, 0.707, you might say, what's the kernel of this matrix? What things can I multiply this by to get 0, 0? And if you work it out, you'll realize that, again, the kernel of this guy, maybe I'll call this one B for now, the kernel of B is also nothing more than the 0 vector. And again, you can see that because of the operation, right? Remember, this is the rotate counterclockwise 45 degrees operator. That's what the function of this thing did. It would take that point and move it over there. It would take that point and move it over there. It would take that point and move it over there, right? It rotates everything 45 degrees to the counterclockwise direction. And therefore, again, how could you end up here unless you started there? Any other point is going to be moved around here, and you're not going to get anything that ends up in the origin except right there, right? Okay, so now you might ask, is there any matrix that has a kernel other than that? And of course the answer turns out to be yes, otherwise I wouldn't be going through this, right? So let me give you an example. Take that matrix right there, 1, 2, 3, 6, and ask yourself, can you multiply this by any vector and get out the 0 vector? Now, of course, we know if we multiply it by 0, 0, we're going to get out the 0 vector, duh, right? That's obvious. But I'm talking about not multiplying it by 0, but multiplying it by something else. And if you play around with it, you realize you can. So here's 1, 2, negative 1. Let's multiply that. 1, 2, dot producted with 2, negative 1 gives us 2 minus 2, which is 0. 3, 6, dot producted with 2, negative 1 gives us 6 minus 6 is 0, so bada boom, bada boom. That is in the kernel of this matrix. We'll call this matrix C. So the kernel of C not only is the vector 0, 0 an element of this, but also 2, negative 1 is an element of this. Can you find any others? I bet you can. I bet if you think it through, you'll realize that another one would be 4, negative 2. That's going to end up giving you 0, 0. And I'll bet that if you think it through, you'll realize that if you multiplied this thing by negative 3, 1.5, you're going to end up getting 0, 0. Okay? So there's a lot of things that are actually in the kernel here. And here is the key insight. The key insight is, what is different about this matrix than the other ones I had before? What is different about this one than the counterclockwise rotation one, than the flip about the y-axis one, than the scaling one, all those kinds of things? And here's the critical insight. This thing, baby, is blue domino columns. Ooh, deep. That is what makes this thing have a kernel that's not 0. These columns are not linearly independent, right? If I think of this in terms of the domino game, here's what I've got. I've got the domino 1, 3. Sorry, it's kind of an ugly 1. And I've got the domino 2, 6. And as you remember from the domino game, these two are right on top of each other, right? Because the second one is a multiple of the first. If I take the first domino and multiply by the second one, the first domino multiplied by 2, I get the second one. Therefore, really, I only have one domino here, not two. And this turns out to be a deep, deep, deep thing that runs through all of linear algebra. And we're going to talk about it in a number of different ways in coming segments and episodes. But for right now, just realize that and this is weird, you kind of have to take this on faith, the fact that these are blue dominoes means the kernel is not just the trivial kernel, which is 0, 0. And you can see that because if one of these is a multiple of the other, well, then you can do something like this, right? You can say, well, let's take 2 of the first one and subtract 1 of the second one, and bada boom, we're going to end up getting the 0 vector. You can't do that if you have yellow dominoes here, right? If you have yellow domino columns, there isn't any way to get one from the other. Therefore, there's no way to multiply one of them by something and the other one by something else and add them and get back the perfect 0 vector, okay? And that plays out in multiple dimensions too, not just 2 dimensions, right? And of course, in higher than 2 dimensions, as we talked about, linear dependence is more than just, is one of them a multiple of the other? You can have it where one of them plus the other one is the third one, right? That also means they're linearly dependent. That's another way to be blue dominoes. So it's not quite as simple as just find one as a multiple of the other. But nevertheless, bottom line is, if your dominoes in the columns are not linearly independent, if you don't have blue dominoes, then you're going to end up getting a kernel that is non-zero. Fun fact.